Okay, so welcome to the third lecture of the day. Today I'm planning on talking about the real numbers. So naturally I wrote down rational numbers on the board because more specifically I'm going to talk about how you get from the rational numbers to the real numbers. Do you guys know how do you get, like, what's the actual definition of the set of real numbers?
Yeah, I don't know.
Anyone? Well, that's hopefully what we're going to learn today. So not much theorems or stuff today, but I guess the aim of today's lecture is to actually give you an understanding of what this set of real numbers is that you work with so often in algebra. Yeah, what's up?
Okay, how about stuff that is ordered and can do stuff that like they can be added, but like they can also be multiplied and also like.
Okay, I'm actually going to write some of this down. So stuff that can be ordered, they can be added. What else?
Multiplied.
Multiplied? Okay, sure. They are a field, so I guess that includes like division as well. And subtraction. Are there any other conditions that we need to make the real numbers?
That's all looks rational.
Yeah, exactly. If we look at the rational numbers, it satisfies all of this. So we need more conditions.
Rooting.
Okay, so we can do like more algebraic things like square roots, cube roots.
So for example, if you square root a rational number, it will take it outside of that field.
So we can have roots of nth roots, however many roots you want. Yeah, this, if you add roots, that'll get you, it actually won't get you to all of the algebraic numbers, but it'll at least be bigger than rational numbers. But this that we have doesn't get you to pi or e yet. Yeah?
There's somewhere in between some numbers.
There's somewhere.
Like take two numbers, the stuff that's in between those numbers, that's the real answer.
What do you mean the stuff that's in between? If you don't have the reals to talk about in the first place, you can't talk about everything that's between these because you don't have the reals yet. Okay, so roots. Okay, so there's two main ways of constructing the reals from the rational numbers, and the awesome thing is that those two different ways of doing it actually ends up with the same thing. There's actually equivalent between them, and the two main ways are the metric theoretic way of doing it, and the other main way of doing it is the order theoretic. Way of doing it. If you go to university, probably like second year algebra, not linear algebra, not algebra, analysis. Once you have an analysis course, they'll probably teach you the metric theoretic way of defining the real numbers. Chances are they won't actually teach you the order theoretic way, but you can learn that yourself as well. Okay, so metric theory. Let's look at what we have so far. If we have the rational numbers, you can sort of visualize it as on the real line, whatever. Just you have rational numbers ordered I need a lot more dots because the rational numbers are actually dense. They do get as close together as you want, but my hand can only make so many dots. So we somehow want to talk about getting closer and closer to a real number. But we can't say we're at the real number because we're only using rational numbers. So we can't say we're there. But we want to talk about somehow getting closer and closer to a real number. So what we can use is a sequence of rational numbers. So let's consider a sequence, an infinite sequence, not just a finite one. Let's say x1, x2, going on for infinity. And the idea of saying that this sequence is getting close to some other value, well, first of all, if you know what that value is, let's say you want to say it's getting close to some number a. How would you write down the fact that the elements of the sequence are getting close to some specific number a?
You put a in between x1 and x2. Is x1 and x2, are they rational, x1 and
Yeah,
x2?
these are rational numbers. This is a real number that I'm trying to get close to.
So do you put a in between two of those, and then you let x1 or x2 tend to a from both sides? Or squeeze it in?
Okay, so when x1 and x2 are tending, those numbers are moving. Whereas here,
They're fixed.
yeah, so these numbers are fixed. So I want to have a sequence of numbers, so they sort of move. In the sequence they move.
Oh, and tending
Alright.
to a.
And they want to tend to a.
Oh.
Yes. Yeah?
Limit of xi as I tends to infinity is
Okay, so the notation we would use is the limit of xi as I goes to infinity is equal to a. Or equivalently, some might write xi tends to a as I tends to infinity. This is just notation. Like, what does this actually mean when we say limit of something is equal to something? Well, it means something like this. What we want to say is that the numbers are getting close to a. So we want to say that the difference between xn and a, so the absolute value, we want to somehow make the statement that this is getting small. So the way we would do that, but we don't want to say that that's necessarily true for the first value or the second one or the third one, but we want to say that as long as you go far enough in the sequence, this is as small as you want. So you would write something like this. For every epsilon greater than 0, there is some natural number n such that this difference is smaller than epsilon for all n greater than n. First time you read that, it looks very confusing. This sort of statement is not very easy to read on the first time that you read it. But think about it something like this. It's saying that I want this xn minus a to be small. Let's say I want this difference to be less than 0.1, for instance. So I want this to be less than 0.1. So epsilon is our 0.1. And what it's saying that no matter which epsilon you choose, for example, if I choose 0.1, I can find some natural number n where this is smaller than 0.1 as long as you've gone past a certain point. So only from n from big N onwards. So you might have that, let's write down this big sequence, x1, x2, let's say up until x100, x101, and keep going. You might have that from this point onwards, that difference is less than 0.1. And the key is that you can make this epsilon as small as you want. So you could say, okay, I want epsilon to be 0.1. You could say, I also want it to be 0.001. And for the smaller value of epsilon, there'll be another bigger value of n, so I might need to go further along the sequence, but at least at some point, it'll still be small. Okay. How are we doing conceptually here?
That's fine. It's just, but you can make a rational number as small as you like.
Yes, so this epsilon, which kind of bounds how big this difference is, you can make, no matter how small you make that, as long as it's strictly greater than 0, at least from some point onwards, the sequence will be that close to your A. Yes?
What is A?
A is some, let's say, some real number that we want to say, what does it mean for that sequence to tend to A?
I thought you didn't have real things.
That's the next step. Okay. Now the next point is, okay, so this is a sequence.
There's nothing to say that A is real at the moment.
Yeah.
Because- And everything you've done could be in the context of rational numbers so far.
Yes, so far I can only talk about the sequence tending towards another rational number. But now, the question is, can we somehow say that this sequence tends towards something without actually referring to A? Can we somehow get rid of A out of this statement over here? And that is where Cauchy sequences come in. So a Cauchy sequence is when you have a sequence which has some sort of similar property to this. I'll write it down soon. So we sort of want to say that the sequence converges. It goes towards some value without actually referring to the value that it goes towards. And the way it works is like this. So we say that, let's say the sequence xn, this is just shorthand notation for that long sequence. That is a Cauchy sequence if the following holds. So it looks sort of similar to the previous definition. For every epsilon, which is greater than 0, there is some big natural number n such that, now previously we would have this thing involving A. And we can't refer to A, we can only refer to elements of the sequence itself. So what we do is actually consider the difference between two elements of the sequence. So let's say xn minus xm should be less than epsilon.
Is there any reason it can't just be n plus 1?
Yes, there is a reason why. I'll get to that soon. Yeah, I'll finish writing this down and then show why that other one doesn't work. So xn minus xm has to be less than epsilon for all m and n greater than big N. That's the definition of a Cauchy sequence. So far, now see, this does not refer to the limit value itself. It only uses the values of the sequence itself. Okay. Now, we had a question in front. Why can't we just say that xn should be close to xn plus 1, so that consecutive values of the sequence should be close to each other? Well, Have you guys heard of the harmonic series?
Yes.
Harmonic series. If you write it down, so the nth term in the harmonic series is 1 plus a half plus a third up until plus 1 over n. So we can consider this as a sequence of numbers. The first one is 1, the second one is 1 plus a half, third one is 1 plus a half plus a third, and so on. We get a sequence of numbers. And you would possibly have heard that the harmonic series goes to infinity. It doesn't actually tend towards some value, it keeps on growing to infinity. And yet, if you consider the difference between two consecutive values of the harmonic series, let's say hn plus 1 minus hn, because of the way it's defined, it's always going to be 1 over n plus 1. And if n is big, this is very small, this goes to 0. So that's why it's not enough to say that the difference between consecutive terms go to 0. You have to say that from some point of the sequence onwards, no matter which two you choose, they have to be close to each other.
So a Cauchy sequence, by definition, converges.
So if you do like third year maths, like you would have a module called metric spaces, and so there you would say a metric space is complete if every Cauchy sequence converges. So it's basically like this actually. If you consider the rational numbers, not the real numbers, just the rational numbers, you can have a Cauchy sequence where the rational numbers tend to square root of 2. But now, it's technically not convergent because square root of 2 isn't in the space that you're considering itself. So the definition of convergent means that it converges to a point in the space that you're already in. So a Cauchy sequence is that. Okay. So now, once you have a Cauchy sequence, every real number, you should be able to get a sequence of rational numbers that gets as close as you want to that real number. So we can sort of define the set of real numbers as the set of Cauchy sequences. Not quite. Not quite, because you can have two different Cauchy sequences getting close to the same value. So you need to define what you mean for two Cauchy sequences to be equivalent. So you might say, let's say one Cauchy sequence is equivalent to another Cauchy sequence if and only if the difference between them goes to 0. So you have a lot of Cauchy sequences made up of real numbers, and you want to consider two of them to be equivalent if the difference between those, the corresponding terms of the Cauchy sequence goes to 0.
So there's a pair. I mean, they're the same. Well, I guess they're infinite sequences.
Yeah. So because they're Cauchy sequences, even if I shift one of the sequence values up, the difference will still go to 0 because in this, on the one sequence, the differences go to 0 as well. So the one way of defining the real numbers is to take all the Cauchy sequences of rational numbers and you consider them to be the same if they go to, what the difference between those Cauchy sequences goes to 0. And then your real numbers is the set of equivalence classes of Cauchy sequences. Okay, so that's one definition. Real numbers is the set of equivalence classes of Cauchy sequences rational numbers. Okay, so that is the metric theoretic way of defining the real numbers.
Can I just ask, the equivalence clause, is that one of the sequences?
Yeah, so there are lots of Cauchy sequences of rational numbers, and we consider them to be the same if you take the corresponding differences and they go to 0. So when we say equivalence classes, we consider all the Cauchy sequences that are the same, we consider them as one unit.
So even if they're different, if the difference is 0, then they're one class.
Yes, if the difference goes to 0, they're in the same class. And each class is considered one real number.
And conceptually, I don't see how. I mean, you're subtracting still rational numbers one from another, and that's what's tending to 0. So, yeah, I'm not conceptualizing how the real numbers are coming out there. Sorry, let's say irrational numbers, for example.
So let's take.
I mean, where does e and pi, those kind of things come out of that?
Yeah. So I'll do 2 examples. I'll do like the golden ratio, what a particular Cauchy sequence going towards the golden ratio would look like, and one that goes towards E.
Yeah.
So how much time? Okay. So continued fractions are cool. Have you guys ever seen that?
Yeah.
Okay. If you actually work out the value of this, what do you get?
5.
5. So the way you would do it is you would say phi is that, and then phi is 1 plus 1 over, and then the same thing, that is actually phi itself. So you can multiply out, you get a quadratic equation, you solve for it, and you get phi. Okay. Now,
But there's 2 solutions to that quadratic.
But what's negative though?
yeah, there are 2 solutions. You have to use the fact that this is 1 plus, and that's something positive. So you have to pick the solution that's greater than 1, and there's only one of those. Okay, now.
Leah, can you do that? Phi is equal to that. You know that continued fraction is convergence. Or how does that?
That's what we're doing now. Okay, so this is not a Cauchy sequence, but we can make a Cauchy sequence out of this. For example, we can say the first value, x1 is 1, x2, 1 plus 1 over 1, x3, 1 plus 1 over 1 plus 1 over 1, x4, 1 plus 1 over 1 plus 1 over 1 plus 1 over 1. So we actually start making this continued fraction, but we cut it off at some point. If you actually work out what these values are, that's 1, that's 2, that would be 3 over 2, that would be 5 over 3. So all of these are rational numbers, and you can keep going, and you can prove that this is a Cauchy sequence which converges towards 5. Or in terms of square roots, it's 1 plus root 5 over 2. Okay. So that is one example of a sequence of rational numbers which tends to an irrational number. Something similar is for E. You may have seen the formula. E is sum from n equals 0 to infinity, 1 over n factorial. Have you seen that before?
Yes.
If you write it out, that means 1 over 0 factorial plus 1 over 1 factorial, 1 over 2 factorial, 3 factorial, and so on. Infinite sum, these pieces that you're adding together go to 0, and they go to 0 small enough for the sum to actually converge. And there's an easy way, whenever you have an infinite series like this, there's an easy way to make a sequence out of that. It's just the sequence of partial sums. So here your y1, or let's say y0, would be the first term. Then your y1 would be the first two terms. y2 is the first three terms. And y3, 1 factorial, 2 factorial, is the first four terms, and so on. And the sequence that you get, these are all rational numbers, because those denominators are all integers. This sequence is a sequence of rational numbers, which tends to this irrational number e. If you actually write down what the value is, that's 1, that's 2, that's 2.5. That will be 6, 2 2/3, I think. Yep.
Yeah.
So they keep on increasing until you don't actually get to E, but when you go to infinity, it tends towards E. Okay. So that is the measure theoretic way of defining the real numbers from the rational numbers.
Is it called metric?
Oh, why is it called the metric theoretic way? It's because a metric space. So a metric space is a space where you have an idea of distance between 2 points in the space. If you take the rational numbers or the real numbers, you can define the distance between two numbers to be the absolute value of the difference between them. So that's what a metric space is. As long as you have a notion of distance which satisfies the triangle inequality, that's a metric space. The reason why this is called the metric theoretic way is that this definition can be pretty much, you can write it down exactly the same way for any arbitrary metric space. Like here, instead of saying that is less than epsilon, I can say the distance between xn and a is less than epsilon. Or here, where that difference is less than epsilon, I can just say the distance between xn and xm is less than epsilon. So this way of defining Cauchy sequences and when it converges can be done in basically exactly the same way for any metric space. In fact, if you have a metric space, so let's say M, let's say a metric space, you can, for any metric space, you can define what a Cauchy sequence is by that definition that we had earlier. And we actually have a definition that a metric space is complete if and only if every Cauchy sequence converges
So
in N.
so the rational numbers are metric space, but they're not completely.
Yes, they're not complete. But for any metric space, even if it's not complete, we can complete it. What we mean by that is we have our metric space, we can enlarge that space, we can put it inside another space which is complete. So let's say that's the rational numbers, that's the real numbers, and it's in exactly the same way that we got from the rationals to the reals. We consider all the Cauchy sequences in the first metric space, and we define the new space to be the set of equivalence classes of all Cauchy sequences. Yeah?
Do the entities classify as a metric space?
Yes.
But you can't do Cauchy sequences to complete them.
Well, you can do Cauchy sequences, but every Cauchy sequence is eventually constant in the integers.
So how would you complete the integers?
So technically, the integers are complete as a metric space. Good. So it's complete if every Cauchy sequence converges, and if it's not complete, we can make a completion. So in this way, the real numbers is the completion of the rational numbers. Okay. So that is the metric theoretic way of defining the real numbers from the rational numbers. Okay. Now the other one is the order theoretic way. And then technically, once you've defined equivalence classes of Cauchy sequences of rational numbers, you have to define what you mean by adding two equivalence classes of Cauchy sequences and multiplying them and dividing them and so on. So you need to define all those addition, multiplication, division, all those operations on that completed space to show that the structure that you used to with the rationals, where you can add, subtract, divide, that they still carry over to this other space. Okay. Now the order theoretic way of doing it, previously you considered the distance between numbers, and you consider when does the distance get small and so on. The order theoretic way, you consider the rational numbers as an ordered set. The fact that there is actually a given order between the rational numbers. Okay. Let's have a subtitle for this, which is Dedekind cuts. Because there was the mathematician Richard, I think his name was, Richard Dedekind, who defined the real numbers in this way from the rational numbers. And a Dedekind cut is defined as follows. Okay. A Dedekind cut is a pair, let's say A and B. So it's a pair of subsets of the rational numbers which satisfy some conditions. The first condition is that they don't overlap anywhere. So if you take A, you intersect it with B, you get the empty set. So they don't have any rational numbers in common. And although they don't have any rational numbers in common, if you combine them, you have to get the whole rational numbers. So A union B would give you the whole set of rational numbers. So those two numbers together, oh, not numbers, subsets A and B, they form a partition of the rational numbers.
So, do they both go one to infinity and the other one to minus infinity?
That's actually basically the idea. So we're not finished with the conditions yet, but basically that's what happens. So the first one, if you have some element A in A, and you have some other rational number, let's say R in Q, such that R is less than A, then R is also in your first set A. So for example, if -2 is in A, everything below -2 is also in A. The fourth condition is similar. If B is in the other set and R is a rational number which is greater than B, then B is also in B.
You said B is also mean.
Well, small b is in big B.
No,
Oh.
R should be in B.
Well, technically what I wrote isn't false because B is in B.
It's
Just not what you meant to write.
It's not what I meant to write, yes. Okay. So, everything in A has to have, in a sense, everything from some point and lesser, and B has to have everything from some point and greater. And then the last condition would be something like if A is in A, then there is some other element in A, let's say A prime in A, such that A prime is greater than A. Okay, now these definitions of a Dedekind cut. What's the idea behind this? I think you've got the idea. If you have all the rational numbers on the line, no real numbers yet, the idea is that you cut the line everything that way and everything that way. So you cut it over there. And then when you cut it and you say, okay, we divide it into everything that's on that side and everything that's on that side, that cutting is the same as talking about the point in the middle. Make sense? But now the point in the middle is not necessarily a rational number. For example, once we have the real numbers, we can say, okay, let A be all the rational numbers where A is less than √2, and B be all the rational numbers where B is greater than √2. And those two of them together make a Dedekind cut, but the middle point is not on a rational number. The middle point is on √2. But this definition over here doesn't actually talk about the middle point in any way. They just say that it's just a characterization of everything has to be everything to the left of something and everything to the right of something. And there's a little caveat, which is the last condition is like a small condition to get rid of degeneracy. You could have a Dedekind cut that's actually at a rational number. So I could have, if I want to have the rational number 3, I could have my Dedekind cut to be A is everything from -∞ up until 3, including 3, and b is everything from 3 to positive infinity. So that's one possibility of a Dedekind cut that defines the number 3. Another possibility is a going from negative infinity to 3, not including 3, and b including 3. So we want these to actually either they should define the same number 3, or we just say only one of them is actually a Dedekind cut. And the way we've defined it here, whenever there's something in A, there has to be something greater than it that's also in A. So this would not be a Dedekind cut, the first one, because the number 3 is in A, but there isn't anything greater than 3 that's also in A. Okay. So the order theoretic way of defining the reals from the rationals is you consider all the Dedekind cuts of rational numbers, and then that's your real numbers. And that's the definition. You do still need to define, okay, that's the real numbers. You still need to define, okay, what does it mean to add two real numbers? So if I have one Dedekind cut, let's say A1, B1, and I have another Dedekind cut, A2, B2, and each of these are supposed to sort of represent two real numbers, R1, R2, how would you define R1 plus R2? You have to give a Dedekind cut somehow made up of these Dedekind cuts. What? So the middle point between A and B here is R1. The middle point between A2 and B2 here is R2. And we want the middle point to be R1 plus R2. Yeah?
Union A1, the union between A1 and overlap between B1 and B2 with respect, or B1 and A2 with respect to B2.
I'm sorry, say that again?
So, open bracket, A1, union B1 and A2, comma B2.
Okay, where did the bracket close?
It closes off to B2. Just as that's the Dedekind cut.
Okay. What's the order? Because you've got a union and an intersection here.
Intersection is in the bracket.
So we've got that. Okay. So the thing about the Dedekind cut is that in a way we only need one of A and B. We don't need both. Because if we only have A, I can define B to be everything that's not in A. So here, A2 is all the rational numbers except for everything that's in B2. Now over here, the second part of the Dedekind is B2, which means that whatever is here, if this is a valid Dedekind cut, this has to be A2. Which would then, that would just be R2. I don't think this is A2, but if it is, it would just be R2. Yeah?
Technical question and definition. Is 4 necessary, or can you get it from 2 and 3, 1, 2, and 3 combined? Or is this a special case that means you do need 4 as well?
Oh, sorry, that actually reminds me, there's a There's another condition I forgot to add, so let me just add it over here. 6, A is not the empty set, and B is not the empty set. Anyway, so can you get 4 from 1, 2, and 3?
Yes, sir.
I guess so, yeah. I think you can.
So there's not some weird thing that to do with fascinating the real, so we can't assume complements.
Ask that question again?
So 4 isn't there because we can't assume things about complements while not knowing what reals are yet.
No, complements are, yeah, once you define what a set is, complements are fine. Okay, so technically 4 is redundant if you know how complements work and you have 3. But maybe ask a question, why did I have to add, oh sorry, that's not equal to. Why do I have to add the condition that A and B are not empty sets?
Because it's not a real.
Because infinity is not a real number. If I don't leave that out, then I could have the Dedekind cut consisting of empty set and the rational numbers, where this would actually sort of be negative infinity. Because my left-hand set is everything on that side, and my right-hand is the whole rational numbers. So that would sort of be negative infinity. And the other one, with the rational numbers and the empty set, that would be positive infinity. If I take that away, I'll just have the real numbers with negative and positive infinity. But anyway, back to how do I define adding to Dedekind cuts? Yeah?
Okay. Consider a real like here and real here. Everything on that side and everything on that side. Could you? Okay, and the rationals there are ordered. So there's a bijection between B's rational and B's rational.
A ordered preserving bijection?
Yeah.
I don't think that's always true, but continue.
So like the smallest one, even though there is no smallest one, but like order that way, pair them up, the sum of those two for each of them, and then.
Okay. So you have part of a good idea there. You take the smallest one there, you take the smallest one there, you match them up, and you just add the smallest one here and the smallest one there, and you match them up in sequence, and you just add them corresponding to each other. Problem is that B sometimes has the smallest element, sometimes doesn't.
Even if it doesn't, like, you can order out. There's a bijection, right? If there is one.
Okay. If you have the one Dedekind cut, okay, let's say that's one Dedekind cut from 3, including 3 to positive infinity, and another one would have B going from root 2 to positive infinity. There is no order preserving bijection between those two. But you do have a good idea of adding the two elements from B, yes?
I think instead of, you just take the set that is every sum of two things that's where one is from one and the other is from the other.
Yeah. So your A, let's say 1, 2, is the set of everything, let's say A1 plus A2, where A1 is in your first one, and A2 is in your second one. And then your corresponding B is just everything that's not in that A. So instead of adding up like corresponding values, you just allow all possible pairs or all possible sums. That does mean that a particular sum will occur more than once, in fact infinitely many times, but because it's a set, that doesn't matter. We just consider that sum occurring once. So that is how you define adding two Dedekind cuts, which corresponds to adding the corresponding real numbers. When you want to define the product of two Dedekind cuts, you have to be a bit more careful because negative numbers. When you define the product of two Dedekind numbers, you have to be a bit careful because negative numbers and positive numbers, and sometimes negative and negative multiply, you give them a positive, it gets weird. But essentially some sort of, you take everything that is in the one set and then the other set, and that's your set. Okay, so once you have all the Dedekind cuts, you define addition, subtraction, multiplication, division, and all that stuff. And the big amazing theorem is that the set that you get in this way as equivalence classes of Cauchy sequences of real numbers, and the set you get on this side by Dedekind cuts of rational numbers, they actually give you the same set as an output answer.
Was it proved?
Yeah. That was, I don't remember who proved it, but it was at some point where, I mean, there was a long time when mathematicians just like, hey, we all know what the real numbers are. And then I think at some point, I don't know which century it was, some mathematicians were like, do we though? Like, do we really know what these things are?
I feel like mathematicians do that periodically.
I mean, they kind of do. Like, do we actually know what these things are? Like, there was a whole thing with set theory. Like, what is a set actually? And can we do these things that we do with sets? Turns out you can't do everything that you want to do with sets. So one of it was how do we actually define the real numbers? And different people came up with different things. The most prevailing is the metric theoretic way and the order theoretic way. The metric theoretic way can be done the same thing in any metric space. The order theoretic way can be done in any totally ordered set. So like the hyperreals also sort of may fall, it has something to do with the order theoretic side of it as well. And any more questions?
Great. So you said something about hyperreals. So can you construct hyperreals using Dedekind cuts or something similar?
Something similar to Dedekind cuts, but not exactly Dedekind cuts. So like we started with the rational numbers, and then Dedekind cuts of those gives you real numbers. You have to have a bigger set, and then sort of Dedekind cuts of those would give you hyperreal numbers.
Can you say that again?
No. Maybe next time. It's something about how the hyperreals are constructed in the same way using Dedekind cuts. And I don't want to say too much about it because I actually don't know what the most common definition of the hyperreals is. I could just like Google it now, but that would take time. I'll come back to you later. Okay, so which version of definition of the real numbers do you like more? That one? That one. Okay, hands up for Dedekind. Okay, hands up for the metric theoretic way. Okay, that's good.
I like this example of E and phi, that kind of thing. But this one makes more intuitive sense in terms of getting to a real number.
Yeah.
One can visualize it a bit better, I think.
Yeah, it's easier to visualize just cutting the line.
In an arbitrary place.
Yeah. But I think like they would teach this way in like second year university maths, because then like while you're teaching it, you actually have these definitions of limits and all these things, and limits are useful for like differentiation and integration and all that stuff. So while they're doing that, they can teach limits as well. Good. So any more questions about the real numbers? Yes?
You have two like open subsets of reals that together an open subset is complement is open. Because you showed you can have it on the rationals. The cuts of real numbers.
Okay.
On the real.
So you want to have the same Dedekind cuts, but instead of rational numbers, you're actually doing real numbers. So
Specifically to open sets.
yeah. And the short answer is no, because the reals are defined as the set of all Dedekind cuts. If I have, let's suppose I have, so these are now Dedekind cuts of real numbers, not of rational numbers. I have A and B. Okay, first of all, what do you mean by open?
Not an endpoint. As in,
So it's
open
an
bracket, open bracket, open bracket, open bracket.
Okay, but if I write down negative infinity to something open and that same thing to infinity, then by definition my real number R isn't in there and it's not in there.
Okay.
So it's not a Dedekind cut of the real numbers because two of them has to make the real numbers together. So this does not count as a Dedekind cut of the reals. Okay, so these are two ways of defining the real numbers from the rational numbers. I think they're pretty cool. And the fact that after you do these operations, you can still add, multiply, divide, that all these things still behave the way you like is pretty cool. But unfortunately, the reals are not the coolest field out there. That would probably fall on the complex numbers.
I would
Yes.
say that this is a real number.
I think it's like exponents and complex numbers nicely.
Yeah.
Like,
Well, not by arbitrary.
Anyways, I think that's that for today's lecture from me. I think there's some Coke and drinks outside.